Okay, so good afternoon, everyone. Welcome to the latest edition of the MetaMAT seminar. So this week, I have the pleasure of introducing our speaker, who is Professor Aaron Welters, who's an assistant professor in the Department of Mathematical Sciences at the Florida Institute of Technology. So he received his PhD from the University of California at Irvine in 2011. Since then, he went on to hold positions in Louisiana State University and MIT before joining the Florida Institute of Technology in 2014. So his interests include both mathematical physics and applied mathematics, with a focus on EM, material science, and dissipative systems. So today he's going to talk to us about Bessmertnyi realizations, representations, and related problems in multiphase composites. So Aaron, when you're ready, the floor is yours.
All right, appreciate the invitation. Thank you for the introduction, Brian. Yeah, so I just want to start off by saying this is joint work with my now PhD student, Anthony Stefan at FIT. He was previously a master's student, and so some of this material is based on work with him. Okay, so just a reminder, most people in this audience know, but I have a certain perspective on what a metamaterial is and how composites relate to it. So let me remind people the definition that I have is metamaterials, are materials engineered to have properties not found naturally occurring in materials, and typically they're made from periodic composite materials. And so this definition, for instance, comes from a good review article by Caddick, Milton et al. On 3D metamaterials in Nature Review Physics 2019. So my viewpoint is that you have physical phenomenon like conductivity, elasticity, and electromagnetism. You combine this with materials such as periodic or random materials, example, photonic crystals. And then when you want to analyze that, typically what you have is there are a couple ways to do it. You could do, explicit calculations of these objects, or you could get representative ways of discussing this systems. And the way to do that is like the theory of composites, which is essentially starting point being like homogenization theory. This leads to metamaterials, multi-scale analysis in mathematics. It's based on averaging principles and cell problems from the homogenization theory. This is then leads to effective media and effective media theory. And so it can be embedded in it. And in there you get effective parameters such as effective conductivity, effective elasticity, and effective permittivity when we connect it with a physical phenomenon. But then this connection between metamaterials and effective media gives rise to a very important problem, applied problem too, is the realization problem. So if I'm given a function of n variables, say z1 to zn, we ask the question of, can we find necessary and sufficient conditions for the function to be an effective tensor, matrix, operator, etc., of an n-phase composite with phases z1 through zn? And so this question is a very important one, and there are several open problems related to this and solutions on this. And for instance, I recommend Graham Milton's paper in 2021 on some of the open problems in theory of composites. And that's what I'm interested in, what I want to talk about today. So as a perfect example of what does a solution to the open problem here look like, let's consider the case of two variables. Okay, so if I have a rational function, 2 by 2 matrix valued function of two variables, z1 and z2, and it satisfies the following 6 hypotheses. It's a homogeneous degree 1 function. It's real. It's symmetric as a matrix. It's a Herglotz function, meaning because it's rational, it has a positive semidefinite imaginary part in the poly upper half planes. It satisfies the normalization condition here. When I plug in Z1, Z2 is 1, 1. I get the 2 by 2 identity matrix. And then finally, the last one, which is a symmetry, is called the Keller-Dykeny-Mendelssohn relationship. And as one can see that this operation of rotation followed by inverse of the rotation, inverting the function and inverting the parameters is when applied twice, gives back itself again, and so is an idempotent operation, and it's a symmetry of the idempotent operation, meaning it's a fixed point of it, okay? In this case, if you have these 6 properties, then the function f is an effective conductivity of a finite hierarchical laminate geometry with 2D isotropic two-phase conductivity, sigma Z1, Z2, and sigma being the conductivity of the 2 phases. But what's interesting is the converse also holds. So this is a necessary and sufficient condition for 2D isotropic two-phase conductivity functions. And this is originally proved by Milton in 1986. So our main research program interest is to build on this connection to this result. We like the statement and conclusion. We want to relate it to more generally when you have, instead of 2 phases, but n phases, what can we do on this open problem? Okay, so the big picture goes as follows, is we want to do the realization problem, this open problem, okay? And the idea is we know that there are different methods for representing an effective, let's say, conductivity or effective operator. And so typically in the past with 2 phases, we had Hergoltz functions and Stilch functions, their integral representations or continued fractions or measures, moments, and some rules related to it, okay? On the other hand, today we're going to talk about and introduce a different viewpoint, which we believe has greater potential for solving some of these open problems for multivariables based on state space realizations. Classically, ones like the Kalman-type is the one we're generalizing here, and it is based on the Schur complement here. So when we consider these problems and the realizability problems, we end up with a certain class of functions called Bessmertny class of functions or the Milton class of functions. And this relates to effective operators, tensors, matrices, and the theory of composites, as we shall see today. Okay, so what is a Bessmertny realization and what is a Schur complement, just to give you a beginning background on the mathematics of it. So down here, 1, okay, is the form of what a Schur complement is. So if you start off with a matrix or an operator that is decomposed into a 2x2 block form, such as you see here, okay, with A being a bounded linear operator on a Hilbert space that is orthogonally or direct sum decomposed into 2 other Hilbert spaces, then as a block operator, it acts in the following block multiplication way, okay? And so the Schur complement of such a 2x2 block is given by this formula 1. So where does the Schur complement come from? What's the motivation for it? Well, it comes from the following here. So if I take and I want to solve a constrained linear system of equations of the matrix A in this following form, where the second component on the output and the H2 Hilbert space is 0, if I solve this, I'm reduced to a subsystem in which the solution of the first part is given by a new linear equation involving the Schur complement, and then the other part is coupled by a coupling term. And so it is really this Schur complement coming up from constrained linear systems of equations that often we see why the Schur complement is a useful object. All right, so then what is a Bessmertny realization? Well, a Bessmertny realization is built off the Schur complement in the following way. So consider an affine linear operator. You consider a matrix pencil. So here we have n variables, scalars, z1 to zn. We have n plus 1 linear operators, okay, or they could be matrices, okay, all of the same size. And so this is just a pencil here too, okay? Then what is a Bessmertny realization is you take the linear matrix pencil and on a Hilbert space decomposed orthogonally into 2 Hilbert spaces as such, and block put the pencil into a 2x2 block form, and then take the Schur complement of the second block, that function that you get is called a Bessmertny realization. Okay? So a simple object, linear pencil, Schur complement, Bessmertny realization. Okay. So now what ends up happening when we want to actually take functions that we don't know are Schur complements, such as this, that is, we don't know yet if they're Bessmertny realizable. Okay. There are certain symmetries that come into play as well. So for instance, if the matrix pencil 2 here has the 0th term here, 0, we call it a homogeneous pencil. If all the term matrices or operators here are self-adjoint, we call it a self-adjoint pencil. If all the operators here are also semidefinite, we call it a positive semidefinite pencil. If when I plug in Z1 to Zn, all equal to the identity, 1, and then we get the sum, so it's A acting on all the ones, is the identity, we say that the pencil is normalized. So in order to motivate the Bessmertny realization in terms of state space realization theory, in our paper here with Anthony, we have a huge table, and this is just a partial table of showing various state space realizations and how in fact they are actually Bessmertny realizations. And so what we say is that the Bessmertny realization is universal in the sense that all the classical state space realizations and all the multivariable realizations, okay, all are Bessmertny realizations. And so the table shows you how. So for instance, if we consider the classic Kalman realization, so Kalman was well known for the controllability, observability, and state space theory. Okay, in 1965, he showed that if I look at a rational function of one variable, which is regular or analytic at infinity, then it could always be put in the form of a Kalman representation as follows. But a Kalman representation is nothing other than a Bessmertny realization in one variable in which the linear pencil is here, and the 2x2 block structure that we take a Schur complement of to get this form is in this block form here. All right, but now for multivariate situation, there are state space realizations in electrical engineering that are well known, and they are the Fornasini-Marchesini realization and the Givone-Roesser realizations. And now there are multiple variables. So start with n variables, z1 to zn scalars, and suppose the function is analytic or regular at the origin. Okay. Then one can write the rational function in the following form here, or in the following form here. Okay. Where now the z in this term are diagonal pencils or a column row vector of pencils. Okay. But it turns out then, if you look at these representations, you see that there are linear pencils Schur complemented. And so they are as well special cases of Bessmertny realization. All right. So this is why we call the Bessmertny realization universal. It absorbs all realizations in state space that we know of currently. And we have a big list in this paper of many more. Okay. So now I want to show you that there's a model coming from the theory of composites for effective, let's say, operators, tensors, conductivity, etc., in which the effective operator or conductivity is a Bessmertny realization of a special type. So this comes from, this is shown in my student's thesis. The proof of the following proposition, but we'll just state it, is in the abstract theory of composites, this is something that Graham has developed over the years. We can consider an isotropic n-phase system. Okay, so the abstract theory begins with a subspace collection, a Hilbert space, decomposed into 3 orthogonal subspaces. Typically, this orthogonal decomposition is related to a Hodge decomposition in PDEs, let's say. And then for each phase, you have a subspace associated with them. So for n phases, we have n subspaces, each one orthogonal to each other, forming a direct sum decomposition of the whole Hilbert space H. And so then we give rise to orthogonal projections associated with each one of these projections, and as such, they represent resolutions of the identity. Now, with respect to this 3x3, this 3 orthogonal triple decomposition of the Hilbert space, you take a linear operator and you create a pencil out of it formed by these orthogonal projections. Okay. Then with respect to this triple decomposition, we decompose that pencil into a 3x3 block operator form. Okay. Now, typically in theory of composite problems, we have constitutive relations. All right. And so the abstraction of a constitutive relation here is the Z problem. So typically we're reminded of the form of, let's say, Ohm's law and electrical conductivity problems here. Okay. Then the effective operator is derived from the Z problem by the relationship as follows. Okay, sigma star takes E naught here and maps it to J naught for every single given E naught and U for which this has a solution. All right. All right. If we solve for the effective operator and give a formula for it, it turns out that it has a Bessmertny realization, positive, semi-definite, homogeneous pencil that's normalized. Okay. And so it's given by a Schur complement formula, and so it is a Bessmertny realization. Here's the explicit formulas of the operators, positive, semi-definite operators involved. It represents a compression of these orthogonal projections to the UE space, respectively. Okay. All right. So this is an abstraction, but there are many, many problems in the theory of composites and related problems in which this structure, this abstract theory of composites actually holds. But to make it concrete, I want to consider the classical problem now of effective conductivity of a periodic n-phase composite, an electrical conductivity problem. So what I'm going to do here is show you how this abstraction applies to this well-known problem. So what do we start off with? So consider the example down here. This whole object, this square here, okay, consider that to be omega. And so in D dimensions, we'll consider a unit cell, 0 to 2 pi d power, so square or cube or hypercube, etc. And then we decompose the cell into n pieces, and those n pieces are where the phases of the composite sigma 1s to sigma n lie, or z1 to zn here. Okay. So if we look down here, this is representing a 2-phase version of it. And so here, this gray will represent the regions omega 1, and the yellow will represent omega 2. And so now we use and represent for the L2 space representations, we're going to need the characteristic functions for each phase, which we'll denote by chi sub j. And then we do their periodic extension because we're thinking of the cell periodically extended in Rn. So our Hilbert space for the conductivity problem, periodic conductivity problem, will be all L2 square integral periodic functions, vectors, d-dimensional vectors. Okay, we have our standard inner product, and then we introduce the average operator associated with these functions. So think of Fourier series analysis this would just give you the first Fourier series, the 0th Fourier series coefficient of the function f, periodic function f. So what is the Zn subspace collection in this regards? Well, it's the Hodge decomposition for the orthogonal triple. So U represents the constant functions. E represents the periodic functions, which are gradients of potentials whose average is 0. In other words, gradient of a periodic potential. J here represents divergent free periodic fields with average 0. This is the standard Hodge decomposition for the periodic L2 space. So what are the P1 through Pn spaces? Well, it's just the functions whose values outside the phase or the region omega n being 0. Well, this forms an orthogonal direct sum decomposition of the Hilbert space H. Okay. And now we have Ohm's law, which is the constitutive relations we're interested in. Okay. Here, the material then, what is conductivity? Conductivity then is formed by this sum over the characteristic functions. Well, that then is exactly the form of Z1 lambda 1 plus ... Zn to lambda n. This is because chi sub j as a multiplication operator acts as an orthogonal projection onto the jth space here, chi j of H. So now the Z problem in this setting is what you would get in homogenization theory is the cell problem. Okay. Well, still just Ohm's law, just decomposed in a special way with respect to the orthogonal triple here of H. So the effective operator then of this Z problem is in fact exactly the effective conductivity. That is sigma naught equals sigma star E naught. J naught equals sigma star E naught. Okay. But what does this mean? That's just the average relationship. You take the average electric field and you map it to the average current field. That's the effective conductivity. But this is then exactly fits within our setting, this abstract setting, which means the effective conductivity has a Bessmertny realization of this form. Okay. All right. And so for the open problem, the realizability problem now, we can see how the Bessmertny realization problem is important in this setting because the effective conductivity has this. It turns out that if, elasticity has the same kind of abstract perspective, so does electromagnetism. And as such, then, effective conductivity, effective elasticity, and effective electromagnetism, for instance, would all have a Bessmertny realization. Okay. So what we'd be interested in now for the open problem is, given a function of n variables, how do I know it has a Bessmertny realization that comes from a Z problem or from the abstract theory of composites? And then from there, we would try to figure out which ones are effective conductivities, etc., right? So that's our problem. Okay, but there are other problems that also have this abstract theory of composites view. And one of them is the Dirichlet and Neumann map. So Graham in 2016 is an editor of a book extending the theory of composites to other areas of science, of which myself and Maxence Cassier and Ornella Matty and several others have chapters in there. And one thing that he advocates is this abstract theory of composites can be used in other areas, and in particular for the Dirichlet-Neumann map. Okay. So we then ask, from that perspective, then, is the Dirichlet-Neumann map, say for an electrical network and a finite linear graph, does it have a Bessmertny realization as well then? And the answer is it does. So let me explain that with analogies from the conductivity in the continuum to the discrete conductivity problem. Okay, so if I go up here, the analogies from continuum to discrete are as follows. The gradient becomes the adjoint of the incident matrix for the graph. Negative divergence becomes the incident matrix. And the reason is there's a duality relation between the gradient and the divergence. Okay. So then what does the conductivity equation become in this analogy? It becomes this matrix equation here. All right. So then in this setting, the discrete Dirichlet problem and Dirichlet-Neumann map can be described as follows. So if I have a graph, okay, G is the graph, sigma is the conductivity, P sub G of the graph represents the points or vectors or the nodes in the graph. E sub G represents the edges of the graph. For example, consider the picture down here. The number of nodes of the graph is M, number of edges of the graph being N, and the number of boundary points in the graph will be B. So what we do for the to define the Dirichlet-Neumann map is you consider the graph being decomposed into boundary points, nodes, and internal nodes. Okay. All right. So given a vector that takes values on the boundary, we look for a potential, okay, taking values on the nodes such that the conductivity equation in the interior is 0. Okay, so this would be Laplace's equation, generalized Laplace's equation in the interior. And then on the boundary, the function is given by f. And so if we look at the analogy here between the discrete and continuum Dirichlet problem, we see this is the discrete analog of the Dirichlet problem, the continuum. So then the Dirichlet-Neumann map in this setting then takes the boundary data and maps it to the current flowing at the boundary. Okay, so that's actually in the continuum would be the analogy of the Dirichlet-Neumann map. Okay. All right. So then it turns out that what is the formula for the Dirichlet-Neumann map then? Well, we do the following. We decompose what's known as the Kirchhoff matrix here, coming from the Dirichlet problem. We decompose it into a 2x2 block form with respect to the partitioning of the nodes into the interior nodes and the boundary nodes. Okay. And then if we look at this setting, this partitioning then of this problem, we see that in fact it's this constrained linear equation. But we don't want to solve constrained linear equations of this form. That's what the Schur complement was used for, if you recall. And as such, okay, we realize that in solving for the Dirichlet-Neumann map, we have that the Dirichlet-Neumann map of a connected graph has a Bessmertny realization of the following form: homogeneous matrix pencil, okay, positive semidefinite matrices K1 through Kn, all right, although this time does not solve the normalization condition, but otherwise has a very similar form. And so then we now have shown that this Dirichlet-Neumann map also has Bessmertny realization. So what we've done is we've given two examples to illustrate that some of the most important objects of study currently in, I'd say, applied math, for instance, dealing with cloaking, you have the Dirichlet-Neumann map, dealing with a theory of composites and effective tensors, you have the effective operator. Both of them have Bessmertny realizations of a special class, positive, semi-definite, homogeneous. So what is one consequence of these representations of being a Bessmertny realization with a positive semi-definite matrix pencil, homogeneous matrix pencil or operator pencil? Well, what it says is I'm going to get certain positivity properties from the Schur complement. So if I look at the Schur complement of a pencil, operator pencil, it turns out that I can represent the Schur complement as a quadratic form in terms of the original matrix or operator A. The importance of this representation is it says that if the original operator A or matrix is self-adjoint or positive semi-definite or as positive semi-definite real part or positive semi-definite imaginary part, then the Schur complement inherits those properties respectively. So if A was positive semi-definite, the Schur complement is. If A had positive imaginary part, then so does the Schur complement. And the proof of this is very simple. It just starts off with the standard block factorization of a operator pencil or matrix, or block 2x2 block operator. Decompose it into the block diagonalized form involving the Schur complement, and then just evaluate by multiplying this on both sides of A and simplifying the block form. So very simple proof. But now the consequences of this simple proposition is very useful and relates to Hergoltz-Nevanlinna Herglotz function. So let us denote the upper half plane by C plus in the complex plane, the poly upper half plane as C plus to the n. All the other poly half planes then are represented in this form for rotation of the upper poly half plane. And so, for instance, the poly right half plane is given by this rotation where theta is 3 pi over 2. And that'll be where all the components of the vector z are positive real parts. We'll represent the positive orthant, okay, in this form, okay, where all the z variables, z1 through zn, are then positive numbers. And then we have the following consequence, okay? So if we have a positive semi-definite homogeneous matrix or operator pencil decomposed into a 2x2 block form with respect to an orthogonal decomposition of a Hilbert space H, and the 2x2 block evaluated at 1 is invertible, then it turns out that A22 of Z block is invertible for every Z in the poly half planes, in any of the poly half planes. The Schur complement of that pencil is then well defined. It's analytic on D. It's a homogeneous degree 1 function, and in particular, it is a Bessmertny realizable function, okay, with a homogeneous positive semi-definite matrix pencil. And what it inherits is the following properties. It's Hermitian. It's positive semi-definite on the positive orthant, and has a positive imaginary part, non-negative imaginary part in the poly upper half plane. And so in particular, this function, which has a Bessmertny realization of this type, is a Nevanlinna Herglotz function. So in the theory of composites, in the two-phase, let's say two-phase composite problem, effective conductivity, these properties that are derived in different ways are often called the analyticity properties of an effective operator, or conductivity, or tensor. And what we're showing is it really is just a consequence of a Bessmertny realization with a positive semi-definite homogeneous matrix or operator pencil. And so that's one use to show why this theory of Bessmertny realizations of the special classes is useful. And so now we get to an open problem related to our original open problem and the realizability problem, okay? And this is the following, the Bessmertny class of functions. So if I have an n variable k by k valued matrix function, representable as a Schur complement of a homogeneous matrix, positive semi-definite matrix pencil, then it is a rational function. It is homogeneous of degree 1 and has positive semi-definite imaginary part in the poly upper half plane. Okay. In particular, it's a rational Hergoltz function, homogeneous. So these functions with properties 1 through 5, sorry for the typo here, are called the rational Bessmertny class of functions. So now we ask the question, can we go from the four properties, can we go from the properties 2, 3, and 4, okay, and go in the reverse direction and say it has a Bessmertny realization of a homogeneous positive semi-definite matrix pencil? Well, the converse then is true for both when n is equal to 1 and 2 variables. Okay, the n equal 2 case when we had real symmetric matrix function was due to Bessmertny in 82. The Hermitian case was then proved in 2004 by KV down here, right? But the problem is actually open for n greater than or equal to 3, and we're interested in trying to prove or find a counterexample to this proposition in the case n greater than or equal to 3. Now, for the theory of composites and the abstract theory of composites, there's a special subclass of the Bessmertny class called the Milton class, in which the function f is representable as a effective matrix of a finite dimensional orthogonal Z subspace collection. Okay. If it is, then it has the properties that it's a rational Bessmertny class function, which is normalized when you put all the phases equal to 1. Okay. Such a set of functions with the property A is called the rational Milton class. So now the question is if you have a function with the properties B and C here, okay, is it in the rational Milton class? And the answer is yes, it is in the case when n equals 1 and 2. The case 1 is trivial. The case n equals 2 in the real symmetric case was proved by Graham Milton in 1987 using a continued fraction representation of the function f of z1, z2. The Hermitian case was solved in 2016 in the book he edited, Extending the Theory of Composites to Other Areas of Science by Milton. The open problem, n greater than or equal to 3, is the most important problem that we're trying to get a handle on for realizability theory of effective operators and matrices. Okay. So what progress have we made in regards to these open problems? Well, we start off with a theorem that we proved, generalizing an earlier proof of Bessmertny using state space representations. So the theorem that we prove in our 2021 paper is as follows. So every rational k by k matrix valued function of n variables, n complex variables, can be represented as a Schur complement of a linear matrix pencil. Okay? In other words, every rational matrix function of n variables has a Bessmertny realization. Okay? Moreover, if we want to talk about does the realization inherit symmetries, the pencils? Because we realize that symmetries are very important from Graham's theorem in 1986. For the realizability problems, we need these pencils to also inherit certain symmetries. And so what we prove is if f is homogeneous degree 1, this is true if and only if we can choose the matrix pencil to be homogeneous. If the function f is real, satisfies this symmetry. This is true if and only if we can choose all the matrices in this pencil to be real matrices. If the function is symmetric, this is true if and only if we can choose the matrices in the pencils to also be symmetric. If we want the function to satisfy the Hermitian symmetry here, this is true if and only if we can choose the matrix pencil to have all the matrices A0 through AN being Hermitian. In addition, if F satisfies any one of these combinations, A through D, this is true if and only if one can choose the matrices A0 through AN to also have the same associated symmetries. Okay. Bessmertny's proof was based on solving linear systems of equations. Our proof and generalization of it uses state space methods, which we'll explain now. So how do you prove using our construction a Bessmertny realization? Well, first of all, you have a procedure for doing the realization. Degree 1 monomials are always realizable. That's obvious. A scalar multiple of a realizable function is realizable. Sums of realizable rational functions are realizable. And so from this, you get linear combinations of realizable functions are realizable. If you want to deal with products, you have the Kronecker product, which is essentially the tensor product for matrices. So if you have realizable functions and you take their tensor, you take the Kronecker product, it's also realizable. So this handles like matrix multiplication issues and stuff. And then finally, inverses, if we have a matrix polynomial, which is not identically equal, not invertible anywhere, is invertible, is not identically equal, its determinant is not identically equal to 0 in the sense that it is invertible some places, then the inverse of it is realizable. With these 5 realization procedures, we can start with a given rational function, k by k valued matrix function of n variables, and we can realize it. How do we do it? First, you decompose it by its numerator and denominator, and you form a Kronecker product decomposition of them. Then we need to convert an inverse into realizable, which it is, if the original Q is realizable. Then we reduce it from that perspective down to just realizing scalar polynomials. Scalar polynomials are realizable if monomials are realizable, and monomials are realizable if simple products are realizable. Well, from our procedure 1 through 5, all of these steps are doable, and so then we have a realization of our original function f. And so this viewpoint is constructive, taking ideas from electrical network problems and theory of composites for taking 2 composites or taking 2 networks and combining them together to get a new effective operator, a new effective conductivity, or a new, let's see, impedance or admittance operator from those operations. So that's what we mean by the state space methods. So for example, what we do is we create a whole algebra for the realization problem. So the basic idea is we have many elementary operations in linear algebra, for instance, addition, products, inverses, and composition. And now if we apply those operations to two Schur complements, we'd like to know if we get another Schur complement. And in particular, if both objects were pencils and you do the operation, do you get another Schur complement of another pencil? And in particular, if those pencils had symmetries, do the output Schur complement pencil also have the pencil having the symmetry? So for example, consider addition of two Schur complements. A over A22, B over B22. If I add those two together, does there exist a Schur complement of some matrix that is equal to the sum of these two Schur complements? And if in addition A and B have certain symmetries, does the C inherit the symmetries? If A and B are pencils, does C inherit the pencil property? And so we actually proved this for a huge class of problems with the functional symmetries A through E. For instance, scalar multiplication, addition, shorted matrices and direct sums, matrix multiplication of this form, matrix inverses, Kronecker products, compositions of Schur complements, simple products, and monomial realizations. We need this also for, as we'll see, symmetric determinal representations. So as an example, consider the following operations. So if I take a matrix A and I take its Schur complement and I add it to a matrix B, I ask the question, is it a Schur complement of some matrix? And the answer is, it is. It's the Schur complement of this 2 by 2 block matrix with respect to the lower block A22 here. So if A and B are, let's say, Hermitian, then so is C by this representation. If A and B were matrix pencils, so is C by this representation. Okay, shorted matrices, we can do a similar computation. Matrix multiplication, we can do a similar computation. Realization of simple products. So for instance, if I give it a constant matrix B that's invertible, and I get two independent variables, U and V, I want to form this simple product as a Schur complement of a linear matrix pencil that inherits the symmetries if B does. And the answer is it does, and it's given by this 2 by 2 block form here. One can compute that Schur complement and see that, in fact, it does give you back UV times the matrix B. All right. So now one application of our Bessmertny realization theorem is we'd like to show that although we haven't gotten to our full realization open problem solution, already with the Bessmertny realization theorem that we just gave, can we apply it to certain other problems in mathematics? And so one application that we had in mind was, which relates to hyperbolic polynomials in the Lax conjecture, is representing real polynomials in terms of a symmetric determinant of a linear symmetric matrix pencil. So let me explain. So we prove the following theorem using our Bessmertny realization theorem. So any real polynomial in n variables has a symmetric determinantal representation. That is, there exists a linear matrix real pencil of this form, such that the determinant of that pencil is the given polynomial. And more generally, this holds for any field, provided the field is not characteristic to. So to prove this theorem, it's actually quite elementary from our results on Bessmertny realization. So the key idea is, if we start off with a Bessmertny realization and you take the determinant of it, the Schur complement determinant formula gives you that the determinant of F is the ratio of the determinant of A over the determinant of its 2 by 2 block, right? So if F was a 1 by 1 matrix, such as P of Z, then P of Z would be representable as the ratio of two determinants. P of Z would be a real symmetric 1-by-1 matrix. So according to our Bessmertny realization, A of Z would be a real symmetric matrix. We could realize it as such, which means if I could get the determinant in the realization of A22 to be a constant, I will have a proof of the Bessmertny of the symmetric determinal representation of polynomials. And that's what the key idea here is explaining. All right. So that is our proof. You use the Schur complement and determinantal formulas. You do a finite number of simple product realizations, and you arrive at a conclusion that P of Z can be represented as a symmetric determinant of a symmetric real matrix pencil. And our proof of this is in our 2021 paper, Short Proof of Symmetric Determinal Representations of Polynomials. Okay, so the simple proof is, I'm going to skim over this because I want to focus on why SDR representations are important in realizability theory. So this is kind of a mind map that explains how the Bessmertny realization theory, theory of composites, realizability problems, and SDR relates to hyperbolic polynomials. Okay, so I'll come back to this in a second. So the reason that SDR representations of polynomials was important is it's related to a conjecture that was proved in 2005 by Peter Lack's conjecture. He conjectured in 1958. It was proven in 2005 using results of Helton, Vinikoff, on non-convexity or non-commutative convexity in linear matrix inequality. So it's a very complicated study here to prove this. But basically what it says is any homogeneous real polynomial of degree D in 3 variables, which is hyperbolic with respect to the vector 1, 0, 0, okay, and normalized to 1, if and only if P has an SDR representation of the following form, in which the matrices here are not only, this pencil is not only real homogeneous symmetric and normal with A1 being normalized, but also the size of the matrices are D by D. So the difference between this SDR polynomials theorem and the Lack's conjecture that was proved is actually the size of the matrices involved. A1, A2, and A3 are exactly the same as the degree D here. And of course, the normalization. So it's very close. So what ended up happening is with the Lack's conjecture being so important and its proof, people were searching for a way to prove more generally the SDR representation of polynomials. The proofs that existed in the past were very complicated. The first one was due to like Helton and Victor Vinikoff using non-commutative variable theory, which is way outside the pay grade of my students' area of expertise. The other examples were using much more complicated theories, such as complexity theory in algorithms, etc. And so what we were able to do with our proof is we were able to give a very simple proof of the SDR representation of polynomials using essentially elementary linear algebra, one that you could give a problem to for, I would say, an early level graduate student taking linear algebra again at the abstract level. All right. So what is a hyperbolic polynomial? So basically a hyperbolic polynomial is one that, with respect to E in Rn, is when you look at the polynomial for every W in Rn, when you subtract off a scalar T, E, it becomes a 1 variable polynomial and it has real roots, and this is true for every single W. The reasons why we care about these hyperbolic polynomials is in the realizability problem, the Milton class generates hyperbolic polynomials. So let me explain here real quick. So if F is a rational in the rational Milton class, then we know there exists a homogeneous semi-definite matrix pencil that's normalized to 1 at E being the identity 1, 1, 1, 1 here. Okay. And then taking the determinant of it, okay, that's Bessmertny realization, we get this form. And now what it turns out is the determinants of these two are both hyperbolic polynomials with respect to E normalized to 1. And so then the question we're trying to consider, given the progress that's being made with hyperbolic polynomials and SDR representations, is can we use the theory of hyperbolic polynomials and SDR representations for trying to solve the open problem for the rational Milton class for number of variables n greater than or equal to 3. And so I will leave this slide up if you have any questions.
Wonderful. Thank you. Thank you for that very nice talk.
Appreciate that.
I mean, I have a few questions, but I would like to invite the others to jump in first if they have any questions.